You ever look up, see one of those massive multi-ton jets just hanging out in the sky and think, how in the world does that work? Well, it's not magic, it's just some seriously clever engineering. And what's really wild is that the basic rules that keep that jet up there are the exact same ones that applied to the very first airplanes. So let's break down what those rules actually are. So let's just strip it all back for a second. Forget the computers, all the different shapes and sizes, and let's ask a really basic question. What are the 5 absolutely non-negotiable things that every single powered airplane has to have to even get off the ground? This is like the fundamental checklist for flight. So here's the plan for this explainer. We're going to start from the ground up, literally. First, we'll hit those 5 essential requirements. Then, we'll connect them to the actual parts of a plane. After that, we'll get into why planes look so different from each other. And finally, we'll dive into the invisible physics, the 4 forces that are in a constant tug of war up in the sky. All right, first up, that checklist. These 5 things are the universal laws of powered flight. I don't care if you're looking at a tiny little propeller plane or a massive jumbo jet, every single one has to tick all 5 of these boxes, no exceptions. And here they are. First, you did lift, a force to actually get it up into the air. Second, you need space, a fuselage basically, to put your passengers or cargo. Third, the plane needs stability, which is its natural desire to fly straight and level without a pilot fighting it the whole time. Then, of course, you need control, the ability to actually steer the thing. And finally, you've got to have thrust to push it forward. If you're missing even one of these, you don't have an airplane. You just have a very, very complicated car. Okay, so those requirements might sound a little abstract. How does a real airplane actually do all that? Well, it turns out each of those 5 needs is met by a very specific, very physical part of the aircraft. The design isn't random at all. Every single piece is there for a reason. And here is how it all maps together. The wings, well, they're your lift generators, obviously. The main body of the plane, the fuselage, that's what provides the space. All those tail surfaces at the back, that's what gives the plane its stability. The moving bits on the wings and tail, the control surfaces, that's how you get control. And of course, the engines, they deliver the thrust. See, it's a perfect match between a job and a part. So, wait a minute. If all planes have the same basic parts doing the same basic jobs, why on earth do they all look so different? Well, the answer comes down to one single, super important word: compromise. Designing an airplane is all about making trade-offs. You can't be the best at everything, so you have to decide what matters most for that specific plane's mission. This quote absolutely nails it. There is no such thing as a perfect wing, or a perfect engine for that matter. There's only the best design for a very specific job, whether that job is flying incredibly fast, hauling heavy cargo, or being super stable for a student pilot. Every design choice you make is a trade-off against something else. Just look at wings. This is a classic example. On one hand, you have the swept-back wings you see on an airliner. They are fantastic for flying at high speeds, but they're kind of clumsy and less stable when flying slow. On the other hand, you have the straight wings on a small trainer aircraft. They provide awesome stability for takeoffs and landings, but they create way too much drag to ever go fast. See? It's a perfect example of that compromise in action. And you can see this playing out everywhere. Look at these 3 very different planes. The Concorde? It was built for one thing and one thing only: pure, face-melting speed. Hence that sharp delta wing. The Airbus A340 was designed to haul a lot of people a very long way, efficiently, so it's got a long body and 4 fuel-sipping engines. And the little Piper PA-28? It's a trainer. It's built to be stable and easy to fly, with its straight wings and single engine. 3 different missions, 3 totally different sets of compromises. Okay, so we've covered the what and the why of an airplane's physical body. Now let's go a level deeper and look at the invisible forces that are always at play. This is the actual physics that keeps a massive machine hanging in the sky. Everything, and I mean everything, starts with weight. This is just the simple, relentless pull of gravity on the entire airplane. It's the one constant force that flight always has to fight against. And the direct counterattack to weight is lift. As air flows over the curved top of the wing, it creates a pressure difference that basically sucks the wing upwards. To fly, this upward force has to be strong enough to beat the downward force of weight. Lift is really the hero of this whole story. But there's always a catch. The very act of creating lift and just moving through the air creates resistance. We call this backward pulling force drag. You can think of it as the villain, the friction of the sky, always trying to slow the plane down. So how do you beat drag? With thrust. This is the powerful forward-pushing force from the engines. It's what literally shoves the airplane through the air, overpowering drag and keeping things moving. So here's where the magic really happens. For an airplane to fly straight and level at a steady speed, these four forces have to be in perfect balance. It's like a cosmic tug of war. Lift has to exactly equal weight, and thrust has to exactly equal drag. The second any of those are out of balance, the plane will start to climb or descend or speed up or slow down. It's a constant, delicate balancing act. And here's the final piece of the puzzle. None of these forces exist on their own. They are all completely tangled up together. Think about it. If you make the plane heavier by adding more cargo, you now need to create more lift to stay in the air. But the act of creating more lift also creates more drag. And to overcome that extra drag, well, you need more thrust from the engines. It's a total chain reaction. So from those 5 basic needs to the 4 invisible forces of flight, you can see that every single airplane is just this beautiful, elegant solution to a whole set of competing problems, a finely tuned compromise. It really makes you wonder, right? As we start looking at things like electric jets, sustainable fuels, even hypersonic travel, what's going to be the key compromise that defines the next generation of aircraft?